In this video, I demonstrate the importance of the budget constraint in learning something about how consumer behavior actually works. So let's come over here and take a look at a too-good example. Now, this is just the budget constraint. And as previous videos have shown, at the optimum, we have the budget constraint holding. I mean, you can just think about the consumer optimum. Got x1 and x2, and here's our budget constraint. And our budget constraint holds because that's where you actually maximize utility. This is the highest indifference curve you can attain inside this triangle. And so this is at the optimum, at the best x1 and x2, this is something that always holds. So why don't we make that explicit? Not only do we have an equality, but we have what's called an identity. And the special thing about identities is that you can take the derivative of both sides and it still holds. So let's go ahead and do that and see what we learn when we take the derivative of both sides. So first of all, let's just take the derivative of both sides with respect. P1 times, I'm going to leave some space in here, dx1 di. Then we get plus P2 times dx2 di, and that equals 1, just taking the derivative of both sides with respect to income. Now let's do some careful multiplying by 1. I'm going to multiply by I over I. I'm also going to multiply by x1 over x1. We can do this to any term we want. It's just not going to change that actual quantity, and we'll end up getting something that's kind of a nice interpretation of what's happening here. Do that over here with x2. Multiply by x2 over x2. Doesn't change a thing. And we can multiply by I over I. Now we can squint really hard and look at what we have here. And it turns out that if we rearrange some terms here, we have something that looks like that, something that looks like that. If you take a really close look at those, what those are shares of expenditures on good 1 in this case, and on good 2 in this case. So we get a share for good 1, let's call that a share for good 2. And if you look at the terms that they're multiplied by, well, these are income elasticities. So this is an income elasticity for good 1, and this is an income elasticity for good 2. And what we see is something that every economist should know, is that the share-weighted income elasticities equals 1. Intuitive interpretation of this is that, on average, income elasticities are 1. An income elasticity that's greater than 0 is a normal good. Now you can see why we call it a normal good. On average, income elasticities are 1. It means that sort of most of the goods, even if we add a whole bunch of goods in here, this is going to be the case. We just do this for a whole bunch of terms. On average, always, we get this income elasticity, share-weighted average, is equal to 1, and that's much bigger than 0. And so normal goods are normal because that's what we normally see in the real world. And this is an equation that gives you this. Let's take the derivative with respect to P1 and see what happens. It's an equation that we can go ahead and do some similar tricks with. So let's go ahead and do some of those tricks. I'm going to use a different color this time so we can see sort of everything that's going to be happening here. I'm going to multiply by 1 over x2. I'm going to multiply by 1 here. I'm going to multiply all the way through by. Now we have an unholy mess of algebraic terms, but let's take some things here and simplify. Notice that this is the share of expenditures on good 1. This term, this first term, is going to be x1, p1, over income times dx1, dp1 times p1 over x1. We'll get a similar term here for x2, p1 over x2. That takes care of all of the terms, and notice that we get another share elasticity type equation. And this is another type of equation that every economist should know. See that the share-weighted price elasticities with respect to a change in the price of a good equal the negative share of this good one, of the good that you changed the price. And so you can see that this will give you another relationship that pins down where your elasticities have to be based on just observable data. You can do this for as many goods as you want, and you get a similar result just by doing some multiplying by 1 and multiplying the entire equations by convenient terms. Now this is a very useful way to analyze what happens to your elasticities and how your elasticities relate to one another. And it's something that you should be comfortable with doing. So I hope that when you go on and work on problems of your own, you can develop some of your own elasticity formulas, especially from any equation where that's an identity. Go ahead and differentiate and get some relationships between elasticities.